Hello, welcome to my tutorial series on learning R for statistical data analysis, especially in health research. In today's lecture, we will discuss Cox proportional hazard model that is used when we have time to event data and we want to see different risk factors associated with time to event data. That is, we are interested in the survival, either we are interested in death rate, hazard rate. That is basically the instantaneous probability of death. So in Cox model, we basically model the uh, log of hazard on uh, different predictors like risk factors or exposures, or even in clinical trials or interventional studies, we see the effect in the survival in different groups with intervention or effect of intervention on the survival of patients. So in either cases, we have an outcome variable that is time to event, and we have event status as well. And we just assume that there is no sensory, uh, and although we can incorporate the sensoring in the Cox proportional hazard model as well. So let's start with lung cancer data. Uh, I have already called these packages we need to install survival and ggplot2 and gg45. These two are needed to construct survival curve. So let's see. Uh, these are the two data set I have created, but we just do the already built-in data in R that can be obtained using survey miner package, and you can see the data online. There is some problem in lung data, but you can, I think it is downloaded. You can see this is our data set. We have time and status and age, sex, and different clinical markers of the patient, and the calories in male or weight loss, or I think these are potassium and phosphorus. These are different biomarkers which are affecting the survival time of patients from a lung disease. And we are just going to see whether the sex and age is associated with the time to event, time to death, basically, and that is either death or survival. One means death and two means survived. So you can just see this is the basic Cox regression model. This is the time data with status, death status, and these two are the risk factors, sex and age. Here we are just assuming as risk factors. So we can see how the sex and age are associated with uh, time to death or the survival. So you can just see the summary. We get the coefficients on sex, that is minus 0.51. It means females have lower hazard than males, and you can see now these are the coefficients. These are the exponentiated coefficients, and these are called the hazard ratio, HR. Basically, the hazard of a male divided by hazard of a male divided by hazard of a female. I think hazard of female divided by hazard of male, as we have two is assigned to female and one is assigned to male. So basically, the lower category to upper category we just see. So the hazard of upper category divided by hazard of lower category. That is this. It means hazard is higher in uh, male as compared to female. And you can see from this as with increase in 1 unit in x is causing minus zero point 0.5 decrease in the hazard rate. So it means the uh, females are less females have more survival than males, and age is positively associated, as it is clear. The in higher ages there are higher chance of deaths as compared to lower ages. And but age is insignificant, but sex is significant. There is a significant difference, as we already noticed in survival curve. We will notice later. Now, when we have a lot of predictors or exposure risk factors, then we can run different models separately using a covariate function. We will just store all variables in a covariate uh, name of the variable. These are the name of variables that is saved in a vector as saved as covariates, and we will apply the sapply function. That is, we are creating a function named x, uh, that is function of x, and x's are basically the covariates. So you can just run this function, and now these covariates are will be treated as x. Now we just need to supply the x and we will get all the models. And why this status and time to death will be the same. So we are just running a univariate model for each variable separately, basically cox and the x and data. So you can just run and see, and we are just summarizing the data. X is summary of X each model, and we are applying wall test, and the p-values will be reported up to two decimal places, and wall test we are also summarizing the test statistic value, and we are uh, finding beta and hazard ratio and confidence interval for hazard ratio. This is lower confidence interval for hazard ratio, and this is upper confidence level for confidence interval for the hazard ratio. And we will be just writing hazard ratio and in brackets the confidence intervals, and then value of the wall test, and then p-value, beta, hazard rate, and wall test and p-value. Basically, we have four columns. But in HR, we are writing the hazard ratio as well as the confidence interval that you always see in different publications. So this is the compact form in which you need the data. So you can just run this command, and I am just saving is it as R, and you can run residence results RES, and we can also convert it to a data frame, and then you will see the result. That is the exact result we need in our publications. The beta coefficients and the hazard rate with confidence interval, and the uh, test statistics world, the z value and the p values. So uh, you can see this axis has significant impact on deaths hazard, and age has also significant impact, and mostly variables are significant except of mean and calories in male and weight loss. These are not as significant factors of uh, hazard rate. Now you can we will just plot the baseline hazard. Baseline hazard is the hazard when all the variables are set to zero uh, or on their mean value in case of uh, continuous variables. So this is the baseline hazard of overall survival from lung disease. You can see the survival is decreasing with increase in time, and there is a higher variation in later times as compared to the starting time. And we can also plot. We can create a data for example, for male and female separately with the mean age. We are setting age as at mean, and we are uh, keeping different sexes. So we will see how we can get the survival curves for male and female after adjusting for age. Uh, you can just we are using survival fit, and then the model we are using, that is basically we are adjusting in start, sex and age, and basically we are setting age at mean, and we are using both values. We are making different plots for male and female. So you can just see this is survival fit. We are estimated. We have now estimated the adjusted survival, and now we are plotting it on survival curve. So these are the survival for male and female when age is at its mean. This is what we call the adjusted survival probability after adjusting for age. This is survival probability for male and female. And you can see a significant difference in the two groups. And the next and most important thing is we always assume that the proportion, the uh, hazard is basically same across uh, different time points. The change in hazard basically that is we called beta, or we just write as hazard ratio. So in which we assume that the second part, that is exponentiated alpha plus beta x, we assume that that part is independent of time. So we need to test whether it is independent of time or not. So we have different methods. One method is a graphical method. We can see uh, how the survival is changing with respect to time, and this second we use Schoenfeld test, residual test, that in which we see there is an pattern of residual with respect to time or not, and uh, it will also provide the test statistic using chi-square test. If that test is significant, then it means the time factor is the proportional hazard assumption is failed. Otherwise, proportional hazard, if the H naught is not rejected, it means the proportional hazard assumption is uh, true. And you can see Cox proportional hazard. That is, we are just checking there is proportional hazard assumption or not. We are just checked for age, sex. The effect of sex is not associated with time. And basically, the association between sex and age is sex and the time is not dependent on time. That is not a function of time. So the p-value is 0.11. It means the proportional hazard assumption is fulfilled. Similarly, for age, it is also insignificant and globally overall for both sex and age for overall medal, there is no time dependency of the proportional hazard. Basically, proportional hazard means if we are changing x1 to x2 for t is equal to some value, that will be same if we take another value of t that is independent of time. Basically, the change in hazard from x1 to x2 is independent of time. We are assuming this. This is called proportional hazard assumption. So if this assumption is not fulfilled, then we need to incorporate the time, and that is called the extended Cox model. If I get time, I will make a video on extended proportional hazard models, uh, extended Cox model, and for now we can plot and we can see how uh, we can see the shear field residual. We can see as all the points are plotted within these two lines, it means there is no specific pattern in the residuals, and we can say that the proportional hazard assumption is fulfilled. Similarly, you can chain for the individual test gives significant result 0.64. So for this is for sex and this is for uh, age. These are the two values 0.11 and 0.65. These two values are these two values just saying that there is no uh, time dependency of the association between age and survival and or the hazard and uh, sex and the hazard. So that's all about Cox proportional hazard model. If you have any comment, you can just write in the comment box. Thank you.